Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.
In the mid-1970s, we were coming out of an energy crisis. 1973, the long lines at the gas stations. Americans looked to nuclear power as a way to have a long-standing energy that was not entirely reliant upon people overseas who were causing us problems. That was sort of how it was thought at the time. 1973, 41 nuclear power plants were ordered by US utilities, a staggering number. There was citizen opposition to nuclear power. Most of you who were around at that time know that. But alone, that opposition was not strong enough to stop it. There were other more important things that slowed down nuclear power at the time. There was the issue of large capital investment regarding nuclear energy plants. It's a huge amount of money needed just to have your first watt. And building was more and more costly. Deregulation emphasized other energy production plant technologies. But building more nuclear power plants was mostly expected until in late March 1979, there was a significant accident that occurred. It was in the very early morning hours at a plant, the 3 Mile Island plant, that was on the Susquehanna River outside of Harrisburg, Pennsylvania. This is a very large plant with multiple reactors on it, over a gigawatt power production. This left-hand side of this slide shows you the very basic schematic of the 3 Mile Island plant. It's has a nuclear core there. You see core written in red, where nuclear reactions took place. I'm going to describe how nuclear reactions take place in a few slides, but creates a lot of heat through fission. And then there's a primary loop of water that's cooling and moderating this fission, and the primary loop connects with a secondary loop on the right-hand side, which heats up, and it's under high pressure, goes to an area that steam is released, drives turbine fans, and then generates electricity for our use at home. Now, something seemingly ordinary happened that morning. You can imagine that at times things would fail, components would fail, and indeed, very early morning in late March, the secondary loop pump lost power. So the pressure and temperature started to rise in the primary loop because it wasn't whisking away enough energy. And then this PORV valve at the very top of the primary coolant loop opened, releasing steam into a holding tank. The backup pumps for the secondary loop turned on, and then they turned off again. And the operators, there was an indicator on the panel that the operators just did not understand, which was one of the contributing factors to this accident. This light, they thought, meant that it was on. The secondary loop was on. The control rods lowered to slow the nuclear reaction in the core. But the control panel erroneously indicated that the PRV valve was now closed. So the operators at that point thought all was under control. So there was some minor mishap, things went off, on, but it was under control. But then there was the steam, water continued to be released through this release valve on the top, and it created what's called a loss of coolant accident. At the time, at that moment, they did not know that they were undergoing a loss of coolant accident, but the machine knew it. And the machine started the emergency injection water. It turned itself on. Operators thought that it was malfunctioning by doing it. And so they turned off the emergency injection water. So more water and more steam got released from this valve at the top that was open. And then finally, after a long period of time, a new shift came on board, in fact. And one of the engineers of the new shift realized that the secondary loop, there was a problem with the secondary loop, and he turned it on. Unbeknownst to the operators at that point, the primary loop was very low on water. The pumps failed. The water was not circulating. The core was heating up and turning more and more water into steam, releasing more through the valve. So there was more of a problem than they even realized. At this point, there was so much loss that steam started to form on the top of the fuel rods. Instead of a coolant water flowing evenly across it, steam was on the top. This is very bad. Very high temperature steam on the fuel rod. The fuel rod has a zirconium alloy cladding on it. And when you put very high temperature water, very high temperature steam on that cladding, it oxidizes, it forms a zirconium oxide plus releases hydrogen. And so that was happening without them knowing at that point. The operators finally figured out that this valve was open and they shut it. But not until 250,000 gallons of radioactive coolant was lost through the valve. That would not have been a disaster in itself, except for the fact that the holding tank, this quench tank for it, burst, ruptured, the diaphragm ruptured on it, and radiation leaked. And the radiation leaked into the main containment vessel. Radiation alarm sounded, and at that point they knew it was an all-out accident and a very serious, potentially serious disaster in the making. Very shortly after that, there was an explosion. They're not exactly sure what happened, but the post-mortem on it all was that it's very likely that it was a hydrogen explosion caused by this oxidation of the zirconium cladding on the fuel rod. But thankfully, this reactor had a very strong 4-foot thick concrete wall containment vessel, and it just caused internal readings to plummet, but it did not breach the main containment vessel. The primary loops then were turned on. Plenty of water was circulating. Core temperatures came under control. A catastrophic disaster was averted. There was an economic disaster and a small radiation leak, but no substantive release of radiation outside, no real risk to the public. Many people were scared by this accident, and it was exacerbated by an extraordinary event. 12 days earlier, the China syndrome was released in the United States, only 12 days earlier. And if you've seen that film, there is a place in the film where one of the persons is saying, what a disaster this is going to be. It can take out a landmass the size of Pennsylvania. Yes, that was in the film. And so 12 days earlier, the governor of Pennsylvania and his lieutenants and so on were really scared. And press conferences, by the way, were also a disaster. There was a disaster all along. And some people, maybe partly tongue-in-cheek, but partly serious, said that if no humans were involved at all, it would have been fine. So, but there's a similar story with this, which was a much more serious disaster. In 1986, this is the Chernobyl disaster. This is an aerial photo of the plant after huge explosions, huge problems. I want to go through the Chernobyl disaster and the human failing and some aspects of design failing on that. So the crew wished to test how long turbines would spin after a loss of main electrical power. This was a test. They had it planned for a while, and then they finally were able to do it. But for various reasons, they needed to disable some safety mechanisms to do this test. Control rods were, so they had a loss of power, they had a loss, a small drop in energy output. They then withdrew the control rods, which were to speed up the fissioning process to boost the falling power, there was a spike in power. The reactor became unstable. There was a design flaw, a positive sort of feedback loop on this reactor. This rising power was much quicker than they expected. They attempted to shut it down by reinserting the control rods, but the control rods had some graphite as part of it, which is a moderator. And what that did was it created more thermal neutrons to aid the fissioning process in the reactor core than they expected. And there was a further spike in the power in their attempts to shut it down. A very hot fuel mixing with cooling water created a spike that was extraordinary in scale. It destroyed the nuclear fuel assembly. There's a nuclear fuel assembly, which is all of the fuel rods in the zirconium cladding sort of packed together in a special way. This steam explosion destroyed it all. Releasing radiation, there's the radioactive elements that were bound within this cladding that were released. A 1,000-ton reactor cover plate was just blown off. That's how serious of an explosion it was. There was a further explosion that was caused by the zirconium steam-generated hydrogen that exploded a short time after. 50 million curies of radiation was released to the atmosphere in this explosion. In particular, the dangerous iodine-131 and cesium-137 isotopes, which I will describe where that comes from in the next slide. 1 curie is equal to 10 to the 7 decays, about 10 to the 7 decays per second. So 50 million 10 to the 7 decays, 10 to the 10, excuse me, decays per second were happening in the air right around this Chernobyl accident. Many deaths and many cancers occurred from this accident. There was at least 30 that died more or less immediately from severe radiation poisoning and the explosion. And many thousands died after that through long-term cancer risks and short-term radiation exposure. And the final tally is impossible to know, unfortunately. Let me describe the physics of where this iodine and cesium comes from. Iodine, I'll first state that iodine and cesium is a health hazard, and it's in the news with regard to the Fukushima plant accident as well. Iodine-131 is radioactive. It has a half-life of about 8 minutes. And the problem is that it collects in the thyroid. The thyroid wants iodine in it, and when it's floating about, it collects it fast. And there's a very high cancer risk when it collects there. This is the reason why the mitigation of this cancer is to take potassium iodide pills immediately. If you take them a day or two too late, a few days too late, it doesn't do much good. You've already absorbed a lot. You need to take immediately. That's why there needs to be excellent communication in times of disaster. And children are particularly at risk. Many thousands of children had this risk from the Chernobyl accident. But if you take these pills, there's a stable form of iodine which then blocks the bad form of iodine from staying in your thyroid. So it's a safety mechanism. Cesium-137 has a half-life of 30 years. It gets put into the soil, into the food chain. You digest it. And over time, the radioactivity of that will cause cancer and other health hazards. So where does this come from? Well, inside this zirconium cladding, this fuel rod pellet, is uranium-235. And when you bombard uranium-235 with a neutron, a thermal neutron in particular, a neutron which has very small amount of energy that's sort of what you would expect from thermal, being in contact thermally with normal temperatures. This plot on the very left shows a neutron coming in from above, hitting the 235. it briefly forms uranium-236, which fissions. So there's other things that can happen, but for this to work, the process of choice is going to uranium-236, which then breaks off into two elements with mass number around 95 for one element, and around 137 for another element. In this picture on the far left, this is krypton and barium. It forms those two elements, and a lot of heat is generated in the process. So using the Einstein's E equals mc squared, you can compare the mass of the beginning state to the mass of the sum of the masses of the final state. There's a mismatch, and that mismatch is energy that gets thrown off into neutrons and into heat, and it heats up the core, and that water coolant in a reactor is what's whisking that heat away, and then ultimately using that energy to drive a turbine and giving you electricity. So this is what's happening, and then you also have iodine and cesium that is around that 130, 137 mark. That is they call it a branching fraction final state of this fissioning process that can take place. And in the bottom right-hand corner of this slide, I show what cesium does. So cesium-137, it has a half-life of 30 years, as I say. It can decay into electrons with very high energy. 0.5 mega electron volt energy is a high energy. And then a damaging further decay of a baryon, 137, down to sort of a metastable baryon 137 down to a more stable baryon 137 through a photon with high energy, 0.7 MeV energy. And as I mentioned in the accidents of these machines, the radiation is released not only by the cataclysmic reaction, like this explosion in Chernobyl, but the zirconium cladding can become brittle and can break and weaken when the hydrogen that's formed from the burning then diffuses into the cladding and creating a brittle situation, allowing leakage of some of the radioactive elements. So what is the impact of these accidents? Well, the United States, it was a shutdown. Utilities stopped ordering nuclear reactors after 3 Mile Island. Many European countries voted to phase out nuclear power after 3 Mile Island and Chernobyl. Sweden, I believe, was the first country to detect the Chernobyl accident when they were monitoring radiation levels. Germany immediately decided to close down their nuclear program, but phasing it out over a long period of time. Belgium, Italy, et cetera. Global interest declined. And this slide, you can see the number of active reactors was climbing rapidly through the 70s, through construction, and then with 3 Mile Island and Chernobyl, and also some economic reasons, it declined rapidly. So for 14 years, that was the way it went. People were creating generation plants, electricity generation plants, and we all lived sort of happily, not knowing really what was going on so much, at least for me. And I was living in California at the time, and Californians are very enlightened people, and they are so enlightened people that they realize that every form of energy has its dangers, and so let's build none of them. And so they didn't like coal, we didn't like gas, we didn't like so on. And I was sitting in my office in Berkeley, and I got an email, which a lot of people in the Bay Area got, which said, "Turn your lights off. There's a stage 2 emergency, and later higher stage emergencies. We don't have enough power, and hospitals need it, police stations need it, and so on." And I'm just go to the next slide to show you what was happening in California. Generally, utilities like to have about 15% reserve capacity versus peak usage in power. And in California, it was in the 80s, early 80s, it was fine. There was 15% or higher. And then there was a population explosion. There was a .com. Everybody was moving to California. It was the new gold rush. Lots of people coming, but no more power plants. And the capacity versus peak demand was falling, and falling rather rapidly. Usually, as I say, usually I like to have over 15%. You were down to 4% in the year 2000. And I'll give you one slide to show you. This is energy generation applications by utilities versus approvals in California. And look at the year in the early 90s, there was effectively nothing. And then there was applications. People started realizing you need more energy. There was lots of megawatts applied for and zero approval for 2 years. And then people started realizing there might be a problem. 1999, there was approval started, but it was too late. So California's largest planning rolling blackout since World War II began to avoid an uncontrollable breakdown of the statewide grid. There was problems with very hot days in San Francisco. I remember that, extremely hot in the mid-June. Serious power alerts with less than 3% reserves, rolling blackouts across the state. The popularity of the Governor Gray Davis suffered dramatically. He won the re-election in 2002, but against what ultimately turned out to be an extremely weak candidate, Republican candidate against him. And shortly after that, he was recalled. Only the second governor in history to be recalled. Now, there were many reasons for the energy crisis. So I built up the energy shortfall as one of the reasons. And in a policy report, it was stated as the number 1 reason. There was a shortage of generating capacity. Everybody knew that. But the regulatory environment in California had changed. There was Enron who was participating, and you know what that can mean sometimes. There was wholesale generator market problems. So there was many reasons why this California energy crisis happened, but no governor wanted this to happen in their state. And you've heard the phrase, there's no atheist in a foxhole. Well, there's another phrase I'd like to tell you about from California experience. There's no environmentalist in a blackout. All these very environmentally aware people say, I want my power now. And I don't care how you do it, give me my power. And you know, their espresso machines weren't working, and you've got to build your power. So care in building infrastructure has the potential to be compromised in crisis times. Don't let the power, if you're an environmentalist, don't let the power run out. I feel like I'm an environmentalist. I think most of you are. If you're here today, you're worried, I think, about the environment. So we're all in this together. We all agree on this, but don't let the power run out. Other states, as I say, noticed this. There was a fast attempt to build capacity any way you can. But then an international story hit. The international story was this IPCC, International Panel for Climate Change, 2001 report, where for the first time it was strongly stated that the warming observed over the last 50 years was attributable to human activities. In the light of new evidence, they say, taking into account remaining uncertainties, most of this observed warming was likely to be due to increase in greenhouse gases concentrations. And this was mainly from CO2, from fossil fuel burning. The greenhouse effect, many of you are very familiar with this, so I will go over it quickly. Sunlight comes through, greenhouse gas don't care. It's a high energy light coming through. It's absorbed by the ground. The ground then heats up and then radiates a lower frequency, a lower energy wavelength. And the greenhouse gases then absorb that and re-radiate back down and create a greenhouse effect and a heating up. So the CO2 and methane and other elements are contributing to the greenhouse gases and heating up the planet. That is the supposition. There is some good evidence for that, which I will spend a very short period of time on. This is some CO2 concentration extraction and temperature extraction from Antarctic ice cores, where over thousands and thousands of years one can see a very good correlation between CO2 concentrations and temperature concentrations. And you might say, well, how are you going to measure temperature from 40,000 years ago? It's done through various isotopic concentrations of oxygen in these ice cores, and that's how they make the connection to temperature. Different temperatures have a slightly different concentrations of these isotopes. So in this slide, I show that the measurements of temperature, global average temperature, increasing somewhat dramatically over the last 100 years. The global average sea level increasing. In the middle plot, the lower plot, the northern hemisphere, snow cover is decreasing. The sea level rising because of the heating up of water and also the melting of ice on land. So the sea level rises are a major concern from global warming, and this was all very much in the news in the early 2000s. My hometown of Clearwater, Florida is in red here, so I was very sensitized to this. If many estimates suggest that it could go up a half a meter in the next 50 years or 100 years, which can really create lots of problems in South Florida and the coasts. And in Europe, Holland, the Netherlands, Britain, and a real tragedy in the making of Bangladesh, which has major flood problems every year, and this would only create worse circumstances for that country. So it was in the news. Fossil fuel is bad. So we have nuclear fuel is bad and fossil fuel burning is bad. Electricity generation is a major source of fossil fuel, as this plot shows. The very right bar graph says, indicates that electricity generation is actually more of a contributor to CO2 emissions than even transportation and driving your cars, although transportation is a huge aspect of this. In this discussion, we're not going to talk about transportation and oil burning and gas, but that is a major issue in CO2 emissions, and perhaps one day we'll be able to handle this through electric cars and other ways to do it. Instead, the focus here is on electricity generation and power plants, and how are we going to rid ourselves of environmentally hazardous forms of electricity generation. Coal and gas, as we see from this plot, are the primary power plants for electricity generation. You see there's a very small slice of oil in gray, and some places still use oil. In Massachusetts, there's a major plant that uses oil burning that they're trying to phase out with wind farms. We look at the energy pie in the United States, and we see that coal is generating 45%, natural gas about 23%, and nuclear 20%. And then we have these hydroelectric sources, which we can't really grow too much at 7%. And then renewables. Renewables at this stage, that stage, we're not in a position to replace coal or replace nuclear energy in any short period of time. So what do we do in our increasing energy demand? And what was determined is that nuclear is starting to look pretty good, given all of these hazards of fossil fuel burning. And a very influential columnist in 2005, after all this had been processed, all of the IPCC reports and time delay from the Chernobyl accident, he had a column that says, we need to start building nuclear power plants again. And he was not the only one that said that. This was a call throughout the entire United States. It was a call throughout the world. There was a global resurgence of nuclear energy interests throughout the world. In the United States, from 1979 to 2007, there were no new reactor licenses requested. In 2007, there were 27 requests for nuclear power plants. 18,000 new people were hired in the industry to meet projected construction demand. It was a boom for employment. It was the heralding of a new era of nuclear power and environmental safety. The world reacted similarly. Sweden, of all places, reversed their 1980 referendum to phase out nuclear power. Belgium did a similar thing where they extended their lifetime of their plants. Germany, which was one of the most anti-nuclear countries in the world, especially after Chernobyl, across the political spectrum, much of the political spectrum, decided to delay plans for phasing out their 21 reactors by 2021 and extend them another in years. And Italy and France were similar. In France, they never lost faith. France was positioning themselves as a major player, and they still are positioning themselves as a major player in nuclear energy export for its economy, hiring lots of people to do that. Joint agreements with China to build plants. And 3 Mile Island, it was stated, it's a plant that had some human problems that we fixed. That was our wake-up call in the United States. And we've learned from it, so now we're set. Chernobyl was everybody else's wake-up call, and they learned from it. And Chernobyl was sort of a ridiculous design anyways, and everybody knows it was, and even the Russians know it now. So, so we move on. Progress looked inevitable until this dramatic tragedy of Fukushima. Let me briefly state what the Fukushima accident. Immediately after the earthquake, Reactor inserted control rods into the core to cease fission, and the backup diesel generators kept power going. All was okay. All seemed to be fine at that stage. However, an hour later, the tsunami arrived. They had a wall to protect itself from the tsunami, but it was 5 meters, and there was no anticipation of a 15-foot tsunami, a 15-meter tsunami wave coming, knocking out things in its path, including the backup batteries. The batteries ran out after a few hours. Arriving mobile generators did not work for several hours, interrupting coolant flow. Temperatures began to rise in the core. It's still heating even if you stop the majority of fission. Cooling water started to turn to steam. The zirconium alloy cladding on the fuel rods was oxidized by the steam, releasing hydrogen. And those big explosions which blew the roof off of some of these buildings were sort of escaping hydrogen that then exploded. Radioactive iodine and cesium that we talked about earlier from compromised fuel rods in the spent fuel rod pools and potentially the reactor core were being released to the environment. The IAEA says that up to 26 microsieverts per hour are being released in nearby evacuated towns. This is about 0.22 sieverts per year. The total amount of radiation that you should expect to receive from natural sources around you, we all are experiencing radiation as we speak, is about that, in fact, for a year, for a lifetime, excuse me. And your lifetime radiation dosage is something like 15 chest CT scans, 100 mammograms, and there's other comparisons that one can make. So it's a fair amount of radiation that's happening, and it's dangerous, and it's well above any safety margins. It's not going to kill people in those towns immediately, but the risk is heightened. People who are very close to the reactor, of course, experience much more than that. And time will tell how much radiation was released, how many people will have been affected by this disaster, reliable specifics to be determined later. Nevertheless, a powerful syllogism has emerged among the people and among politicians. This was a very serious accident. So the syllogism also has as one of its premise that if you can't trust the Japanese, who can you trust? If I were to ask if I wanted to live next to a nuclear power plant in the world, I'd probably want to live next to a Japanese one. There's a tremendous amount of trust in Japanese know-how, Japanese engineering, and so on. So the result of this is that not in my backyard, never. So in the State of the Union address given on January 25th, Obama stated that he wants to challenge Americans by the year 2035 to have 80% of America's electricity from clean energy sources. Now, clean, what is clean? So he goes out on a limb and he describes perhaps describes what clean is. He says some folks want wind and solar, others want nuclear, clean coal, and natural gas. To meet this goal, we will need all of them. And I urge everybody to fall in line. So we need all of them. This is an extraordinary statement. Natural gas is a clean energy source? This is very confusing. In 2001, nobody would have said that. But in 2011, the President of the United States is saying that. Did he really mean it? So in a conference call to reporters, the Department of Energy Secretary, Steve Chu, said that under Obama's definition of clean energy, about 40% of our nation's electricity is already complying. And he stated that many old and worst polluting coal plants will be converted to gas, and that 80% of clean energy by 2035 will be an ambitious goal. But then he asks rhetorically, is it over the top? No, it's not over the top. We can do it. So there's lots of discussion in the energy community about what's really meant by clean energy. And it created somewhat of a confusion. And on March 30th, just a few weeks ago, at Georgetown, in his energy security speech, Obama said, now in terms, so he talked about energy in a global perspective, and then he said, now in terms of new sources of energy, we have a few options. The first is natural gas. Recent innovations have given us the opportunity to tap perhaps a century's worth of reserves in the shale under our feet. So the Obama administration is very keen on natural gas and shale gas as a way to improve our carbon footprint, if not completely eliminate it, at least improve it, without much discussion of some of the other forms of energy. He did discuss other forms of energy, but natural gas is something that can happen now and fast. So what is this shale gas? In the United States, we have about 4.5% of known reserves of natural gas around the world. And we've tapped a lot of it. You know, the low-lying fruit, we've tapped a lot of it. But there's gas trapped thousands of feet below the surface in shale rock. Shale rock is this sedimentary rock that's packed very, very tightly, and if you hit it, you can break it along horizontally into thin slabs. So they have these drills that go down very far through the sandstone all the way down to the shale, and then horizontally they can drill through. And then they hydraulic fracture the shale rock. Very high pressure, water, sand, chemicals. Chemicals are helpful, that then release the gas that is trapped in the shale rock, bubbles forward up through the well, and you collect it, and that's your natural gas. And this looks great, right? I don't have to rip apart the surface of the earth. I just drill down, and I move around in shale rock, and I get all this gas. And this is something that the Obama administration is looking at very, very carefully. There are some concerns about contaminated water. There are reports of benzene showing up in taps. And it's a chemical that's used in fracturing, hydraulic fracturing of shale rock. And it can create some health hazards. Now, where is shale rock found in the United States? Well, God was nice to Michigan. It's It looks as though the boundaries of Michigan were created by Shale Rock. So there's a large source there, and there's large sources all the way up and down Pennsylvania, Appalachians, and in the West. And this gas exploration is what is going to happen in the future. I think there's no two ways about it. In the near future, gas plants, this kind of extraction is fast, and gas plants are relatively fast and relatively cheap to build. Now, why is this better than coal? And the simple answer is that you get more bang for your CO2 buck. So methane, the way you create heat from burning natural gas is you take methane, which is a carbon and 4 hydrogens attached to it, and you put a lot of energy into it, and you break the bonds, and there's oxygen floating around, and you then remake bonds of the carbon with oxygen to create CO2. This is that terrible gas that creates global warming, and water, and heat. So the exothermic reaction, so you break bonds, and then you attach bonds. This is burning, create heat, and you make steam, and you drive your turbines. Now, the reason why this is better is just an accident of chemistry. Coal is a very complicated mixture of hydrogen, oxygen, nitrogen, sulfur. So this is where the sulfur dioxide comes from. That coal plants are doing a good job of ridding themselves of now, mostly. There's bitumen coal, there's anthracite coal, the different compositions in different places on the globe. You have different compositions of coal. Some of the nastiest coals in Germany, which they are chewing up and burning and creating lots of CO2 from the German coal. We have very high quality coal in the United States comparatively. But the amount of CO2 that is made per unit energy is larger with this chemical composition in the burning of the coal compared to methane. And here's a plot to show that relative difference. So for every megawatt hour of energy created through coal burning, there's 564 pounds of CO2. But there's only 331 pounds from natural gas. So natural gas is almost a factor of 2 better than coal in CO2 emissions, which is a very pleasant prospect for reducing CO2 emissions. But there are challenges for natural gas. One challenge that Europe knows about very well is that Russia controls a lot of it. And when Russia wants to flex its muscles, it shuts off the gas. And there's pipelines to the former Soviet bloc that have suffered from the shutting down of gas pipelines from Russia as a political tool. Iran and Qatar have lots of natural gas capacity. The reserves in the US are not as copious as coal. We will get to coal shortly. The extraction is getting progressively difficult. As I say, we have to go to the shale rock, and it could be creating hazards for groundwater due to this hydraulic fracturing. But there's lots of R&D going into shale rock gas exploration, and one can only assume it will get safer over time. Some of you probably have seen this New York Times article just a few days ago saying that natural gas is, you have to account for everything when you talk about global climate change issues, and the release of methane. The release of methane can happen during the extraction process. And methane is worse than CO2 for climate change. It's a worse greenhouse gas than CO2. So in that process of extracting the natural gas up through the wells, if it leaks, one has a problem. And that methane goes up in the air, but it disperses relatively quickly compared to CO2. So in some aspects it's worse, in some aspects it's not. So this recent Cornell study showed that there's a lot more methane escaping during this process than people thought before, and if you take it all into account, maybe it's even worse than coal. But I don't know if people have done equivalent study on coal, and the coal extraction process has similar issues. Transporting gas is very expensive. So if you want to transport gas a long distance, Pipelines are not so good, so you have to set up a worldwide liquefied natural gas market, which Qatar has attempted to do and is doing somewhat successfully. And it's expensive. It's very expensive, but it's helpful. I think even Japan is using this liquefied natural gas to help meet their energy demands, given the reactors being offline. Less than 10% of the natural gas market in the world is in this process, but that might increase over time as the world changes. So now let me talk about a true renewable source of energy. Now, there's not enough time to talk about all the renewable sources. Solar would have been a very good one to talk about, but the new darling of the renewables has to be wind. And we're wanting to create huge wind farms off Nantucket, huge wind farms in Michigan, off in the Great Lakes, etc. Wind is free, it's clean, it's plentiful, we all feel it. Natural gas was good, but this would be even better. If we can tap the energy of the wind, by all means, let's do it. And well, windmills look nicer than smokestacks, so that's probably okay too. And in some places, it's a very large fraction of their energy generation. In Denmark, it's 20% of their electricity is from wind. Now, here's a very simple view of a windmill. I want to describe where it gets its power from and the scaling of wind speed and the size of the blade for wind power. So in this equation, the first term in parentheses is the energy per block of air. So think of it, the block of air as having some mass m, and then there's a kinetic energy with the wind speed of v. And so you have a certain amount of energy associated with a block of air moving along. The number of blocks of air per cubic meter is given by this variable n. This is sort of the density, how much air is really passing through a windmill. And then the volume of air that is traversed in some unit time t depends on the speed of the air. So some column of air will pass through a windmill an amount of in the time t proportional to that length, velocity times time, times the area of the windmill. And power is how much energy can you deliver per unit time. So then you divide by that time. So energy divided by time is power. The power of a windmill is proportional to the cube of the wind speed. So it's, you gain a lot by higher wind. And windmills are borderline for being good electricity generation in the most favorable of circumstances. And so you have to maximize this. You want the highest winds and you want the largest blade you can, because it goes by the square of the blade size. So stronger and less turbulent winds are higher up, and very tall, big blades. The windmills that are on your roof or in your garden are unlikely to pay off economically, but you can feel good that you have less CO2 emitted. Where to build windmills? Well, this is a plot of wind speeds 80 meters in the air. That gives you an idea of how high people want to build windmills. 80 meters in the air in the central United States, northwest Texas, straight on up. Very high winds, greater than, in some cases, greater than 8.5, 9 meters per second winds that are average annual winds. I would not want to live there with those kind of high winds. There's also very high winds in the Great Lakes. They're very smooth, nice winds in the Great Lakes and off the coasts. The problem with the coasts is that you need shallow water because it's extremely costly to anchor a windmill in very deep waters. There's no deep horizon windmill. There's only low, shallow water windmills. And so the Atlantic seaboard, very close to the coast, is a pretty good place for it. The Gulf of Mexico would have been perfect because it's shallow all the way to Mexico. But well, very far off the coast of Florida, it's shallow, but the winds are not very high there. So the places that people are looking are the Great Lakes, the Atlantic seaboard. There's the most famous wind project in the United States is the Cape Wind project off of Nantucket. And there's places all over the United States where they're popping up. And every place, more or less, that they're popping up, there's a lawsuit or complaint filed. And it's in the lawsuit, even the Kennedys were part of the lawsuit in Nantucket, I think. Highly environmentally sensitive people. But they cause, this picture looks good out your back door for a day or two. But after a week or two, you're not sure if you like it. Wind is not the silver bullet. I just want to make two quick cases on that. The costs are still high, probably double what many estimates are that they're double the price of getting electricity, energy from more traditional sources. But they survive by very heavy subsidies. And the wind industry and proponents will tell you, and probably rightly so, that there's lots of hidden costs from other forms of energy that are not immediately seen, but do play out in our society. And so the subsidies are warranted. There's also the complaint that wind is intermittent and not viable in many places. And the response to that is that it can nevertheless add to the power grid. And anything that adds to the power grid is good, especially that which does not create greenhouse gases. It was never, and no wind proponent I think would claim this, contemplated to be the only power source on the grid, or perhaps even the majority power source on the grid, but a very good contributor in places where it works well, high wind areas. And there's others which I won't go through. So finally, let's comment about clean coal. The United States has lots of coal. We are by far the highest reserves of coal in the world. I think we're about double the second highest reserve, which is China. We could have energy independence from coal for centuries to come, probably, for at least a century. We should think long and hard about how we can make coal work in our society. Can we make coal work? A lot of research should go into that. And in any ways, even if we decided we didn't like coal and we're going to do something else, China likes coal, and they're going to build them anyways, coal plants. And their energy needs are going to vastly outstrip our energy needs. And so if we want to participate in a global energy world that is safe and clean, then we should probably participate in the coal industry and the coal research and development. There's a nice report on this in Atlantic by James Fallows recently. But as we've seen, coal is nasty from several different fronts. Scrubbers and technology are doing much more to clean up coal, but there's still many pollutants in the cycle, in the coal cycle. And carbon capture and sequestration is generally what is meant by the term clean coal. And so I will spend one slide on that. Carbon sequestration is difficult. And if you're here on Saturday Morning Physics a few weeks ago with the exploding lakes of Africa, you might have second thoughts on carbon sequestration from that point of view as well. But this is how it works. You have a coal or biomass plant right there in the center of this figure, burning coal with this fuel, creating electricity, and thereby creating CO2. CO2 is captured, and then as my son, I'm sure, very much appreciates, much of it is sequestered into soda cans. And then it's sequestered in other places. It's used in some industrial processes. But then there's a lot left over. And that leftover either goes in the atmosphere or we do something with it. And we can, one way to do it is to, and this graph has this is actually also from the Department of Energy, has several different usages that are stated on the bottom of the graph that you might not be able to see so well. But the CO2 can be used to displace methane from coal, so it can be sort of a coal gas type of extraction process using CO2. It can generate higher efficiency in extracting oil out of oil wells. and then you can by displacing trapped oil. But you also want to sequester it, and there may be ways to sequester it stably over very long periods of time, deep in these saline formations. Now, how well can this be done? It's hard to know, and there's a lot of research and development on it. This is from a recent report from the Department of Energy on carbon capture and storage R&D overview. This gives you a sense of the challenges that we're facing in clean energy is the carbon capture process. If we really do want to use coal, be energy secure, and carbon capture, we're facing a big uptick in our power bills potentially, which we may be willing to pay for. So in this report it says, as an example, today's commercially available carbon capture technologies will add around 75% to the cost of electricity for a new pulverized coal plant and around 35% to the cost of electricity for a new advanced gasification plant. So a gasification plant is an attempt to separate the bad stuff earlier, the CO2 earlier before the burning. This is a rather large increase. The Clean Coal Program is aggressively pursuing developments to reduce these costs to less than 10% of it, and less than 30% increase in the cost of electricity for pulverized coal energy plants. So we have ways to do it. There is debate about how long we can sequester carbon, but we have techniques, and it can happen. So final slide is, and the answer for our energy future is, and of course I can't give you that answer, and nobody can. It's, there's many options and many trade-offs, and most energy experts will tell you, I don't know one that won't tell you this, is that it will take the work and contributions from many different angles and almost every angle to meet our future energy needs. And there can be mitigation and progress in environmentally friendly energy and safe energy in every sector. Coal, natural gas, nuclear, etc. Every one, there's R&D that goes to making a better energy source. But within that context, there's no unique answer. And things change year by year, week by week. And so you have to ask yourself questions like, do you mind less environmental impacts of coal mining than various risks of nuclear? Is energy security more important to you? Are you more concerned about the visual quality and perpetuating whooshing sounds of windmills? I've read lawsuits, depositions of people living next to windmills who are going insane. Or at least they claim they're going insane. And because of the sound and the problems and the flickering of light. The sun will come through the light and can flicker. So they're building further and further away from homes, and there's ways to mitigate that. Do you think paying twice as much for your electricity and energy as an environmentally friendly and good investment to make? Would you think that if you were poor? Poor people die by not being able to pay for their energy. So what to do? And the answer is largely your value system comes in almost as much as science. Our values will dictate what we wish to have, and it will vary from place to place. We may wish to burn and sequester coal in Arkansas and maybe set up wind farms in Nantucket and various places. Trying to be energy responsible and environmentally responsible, we can develop solutions. And the solutions that we ultimately implement in Michigan and the United States will certainly depend on your informed decision making just as much as on science. Okay, thank you.
Saturday Morning Physics is sponsored by the M. Lois Tiffany Endowment, the Hideko Tomazawa Endowment, the Physics Department, and by gifts from friends of the program.